Okay folks, this week we're performing a Friedel Crafts acylation. And why are we even doing this reaction this week? Well, probably by now you've learned the reaction in class. And so today we'll practice it in the lab. It's a great way of making new carbon-carbon bonds. Really a lot of organic chemistry too. We're asking, how can we make new carbon-carbon bonds? This is super important, to make drugs, but, other industrial chemicals can use this type of chemistry, polymers, many other types of important chemical reagents. It is an example of electrophilic aromatic substitution. So a couple weeks ago now, when we made methyl orange, we did the nucleophilic aromatic substitution. Now it's time to try a different type of substitution. Now folks, bear with me through this mechanism. It's been about 2 years since I've thought about this type of chemistry, so if I make mistakes, keep an eye out on it. I want you to check me here. Let's start with our first reactant. Here we go. And enter our catalyst. Our catalyst is a pretty great electrophile here. All those chlorine atoms kind of doing that electron withdrawing, making that aluminum center pretty electronegative. Which is why lone pairs can kind of easily perform a nucleophilic attack. Let's see what happens. Here we are, folks. We did that nucleophilic attack. That aluminum negatively charged, the oxygen positively charged. Our charges are balanced. We're good to go. Now, of course, this oxygen isn't in a favorable state. It's pretty electronegative. So it's not going to remain positively charged for very long. And so we have this kind of cleavage of a bond in this next step to bring the charge of that oxygen back to neutral. You'll see that again our charges are balanced, but now we're left with this acylium ion. It's positively charged but resonance stabilized because we can drop this lone pair down to share that positive charge across the carbon and the oxygen. We're not done yet, folks. Enter reactant, number 2. And we have a pretty good electrophile here. So something that's, not the strongest nucleophile, even with our donating methyl groups here, can do a pretty good nucleophilic attack. Bam. That resolves the issue of the positively charged acylium. Sorry, these atoms got a little bit close together here, folks. And my picture's blocking it. That's AlCl3. This methyl group, is not bonded to the aluminum here. I apologize for that. So we're almost done now. We just need to basically regenerate our catalyst and form our final product. So we have this proton here that normally wouldn't be particularly acidic, But if we have loss of that proton, we can complete the conjugated system across the entire molecule. That's pretty favorable. We've talked about this before. So that's definitely going to happen. At the same time, at this point in the reaction, folks, we're also going to follow up with a workup in half concentrated HCl. So that will kind of help push our reaction to the finish and will kind of decompose the catalyst as well. So let's regenerate that catalyst. Let's grab a proton. Let's complete that conjugation and see what happens. We've completed the conjugated ring. We now have that carboxylic acid group. And we've regenerated catalyst at this point. Of course, at this point we also did our workup. So this will kind of help decompose the catalyst and stop the reaction at this point. And that's the mechanism. Wow, that was terrible. I haven't thought about that in 2 years. Let's pray I'm right. So some things to mention about the protocol that'll be important this week. We are performing this experiment under what we call dry conditions. I'm going to have to dry off that methylene chloride, and we're going to be performing the reaction using an inert atmosphere. If we get water into the system, it'll decompose that catalyst before the reaction ever happens. So in the protocol, we got to make sure we keep that balloon full. And we need to make sure as well that we're just opening and closing our reaction vessels quickly as possible. The same thing goes with the catalyst bottle that you will be provided. A lot of this reaction is going to be performed in an ice bath. And when we're adding the catalyst especially, you'll see we add it bit by bit, and we make sure that the ice remains in the ice bath. This reaction is pretty exothermic, so we want to make sure that we're not heating the reaction. We want to kind of keep this nice and cool for the reaction to go forward and not kind of degrade any of the product along the way. I know there's a lot of different types of HCl hanging around in the lab. Let's make sure to use the right one this week. I'll make sure it's out in one of the hoods. It'll be half concentrated HCl. Basically, just half HCl, half deionized water. And pay close attention to the protocol. There's a lot of kind of detailed steps in this one. So make sure you're really reading carefully and trying not to rush through lab. Additionally, you'll see at the bottom it says, place your product in a flask and label that flask. This is our first 2-week reaction. The product of this week is the reactant of next week. So label that with your group's initials, something else that'll kind of distinguish your reaction from other people's reactions. And we'll leave that in one of the hoods. I'll make sure it's nice and labeled so no one bothers our products this week. Let's finalize up the green chemistry that we've been discussing all semester. Here are the last 2 green chemistry principles. This is less important for us, but it's probably pretty important in industry. Real-time analysis for pollution prevention. Do we know the environmental effects of the products we're making? We're not making products on massive scales, so we don't need to worry about this too much. But in industrial settings, they're making like tons. By tons, I mean like the weight tons of products. And we have to ask, if we're making these products, how do they impact the environment? Additionally, we should be practicing inherently safer protocols. We should not be doing chemistry that is dangerous to ourselves, or we should be kind of minimizing the times we have to do dangerous chemistry. So we prevent accidents, and we protect ourselves. That's all for this week, folks. See you in lab for our first 2-week experiment. I'm super excited. I hope you are too.